By this point, we've already built confidence intervals for estimating the mean, but there are actually two different types. The first are z-intervals, in which the population standard deviation is known, and these are, of course, the types that we've covered so far, but they are uncommon in real life. I mean, if you don't know the population mean, then why would you know the population standard deviation, right? Now, in these types of intervals, the population standard deviation is used to calculate the standard error, as we did in the previous lectures, and the standard normal distribution, or the z-distribution, is used to calculate the critical value, which again we already know. But there are also t-intervals, in which the population standard deviation is unknown. Now these are more realistic since you only have data from the sample to work with. In these, the sample standard deviation is used to calculate the standard error, and the student's t-distribution is used to calculate the critical value. So the process is very similar, just with a few minor tweaks in the inputs and the calculations. Now, as a reminder, both require the original populations either to be assumed normal, which isn't always possible, or for the sample size to be greater than or equal to 30, so that the central limit theorem applies. So in the next few lectures, we'll introduce the t-distribution and then calculate confidence intervals with an unknown population standard deviation. Alright, time to talk about the student's t-distribution, which you'll find is refreshingly straightforward. T-distributions are just like the standard normal distribution, but with fatter tails. Now, in the case of the standard normal distribution or the z-distribution, there's only one, which is described by its mean of 0 and standard deviation of 1. But t-distributions are a family, and each member is described by its degrees of freedom, which for now we can think about as being the sample size minus 1. So let's start by looking at the z-distribution, which is this one right here, and then overlay the t-distribution with 1 degree of freedom. As you can tell, the shape is practically the same. It's symmetrical with most data around its mean in the center, and then it flares out in tails. But the tails for the t-distribution, like we mentioned, are fatter. In other words, there is more data at the tails. For reference, in the z-distribution, 99.7% of the data lies within 3 standard deviations from the mean. We know this from the empirical rule by now. But in the t-distribution with 1 degree of freedom, however, only 79.5% of the data does. And the reason behind this is actually very logical. 1 degree of freedom in this case means a sample size of 2, so it is more probable to get a sample mean further away from the population mean than if you had a larger sample size. And we can see that illustrated here. This is the t-distribution for 3 degrees of freedom, and this is the t-distribution for 10 degrees of freedom. So as the degrees of freedom increase, then the t-distribution approximates the z-distribution, making them practically identical for samples of 100 or more observations. Alright, now that we know all about the t-distribution and how similar it is to the z-distribution, time to introduce Excel's t-distribution functions, which will also look familiar. We have the t.dist, t.inv, and confidence.t functions that we'll be using. The first, as you may have guessed, returns the cumulative probability or probability density at a t-score from a given t-distribution. So in the arguments, you specify the t-score, the degrees of freedom for the t-distribution that you'll be using, and whether you want the area under the curve or the height of the curve, which again, most of the time we'll want the area under the curve unless we want to plot the distribution itself. The second returns the t-score from a given t-distribution at a specified cumulative probability. And this is a formula that we'll use for calculating the critical value for our confidence intervals. And finally, the confidence.t function returns the full margin of error for a specified confidence level and standard error. So the arguments again are alpha for the confidence level, and then the standard deviation of the sample, since we don't know the standard deviation of the population, and the sample size, both of which will be used in calculating the standard error, and the sample size will also be used in calculating the degrees of freedom for the t-distribution to be used. So again, we'll revisit these once we actually start applying them, but you will notice that they're very similar to the normal distribution functions. We're just using the degrees of freedom to describe the t-distribution instead of the mean and standard deviation to describe the normal distribution. Alright, I think we're ready to start calculating confidence intervals with the t-distribution, which is whenever we don't know the population standard deviation. And the good news is that estimating a confidence interval with the t-distribution is just like the z-distribution. You just use the sample standard deviation, or S, instead of the population standard deviation, and use the t-distribution to calculate the critical value instead of the z-distribution. So if we revisit the formula that we'd seen for calculating a confidence interval for the z-distribution, you'll see that those 2 points are the only thing that changes for our new formula. We have t instead of z, and s instead of sigma. So if we want to calculate our confidence interval for our employability scores like before, with an alpha of 0.05, now we have all the data that we need just from our sample. We don't have to pretend like we know the population standard deviation. So we can plug in the point estimate of 239.9 and just calculate the standard error by dividing the sample standard deviation, which is s, by the square root of the sample size, which is n, and all that's left now is the critical value. And for that, we can use the t.m function, which will return the t-score at either alpha divided by 2, which will return a negative value, or at 1 minus alpha divided by 2, which will return the same value but positive, which is what we did in this case, returning a value of 1.98. So we plug that in, and then we just calculate the margin of error and our confidence interval. And we could have also just used the confidence.t function and saved ourselves a few steps here. We just specify alpha, the standard deviation of the sample, and the sample size, and voila, we get our margin of error. It really is that simple once you understand when to apply each formula and what everything means. So let's jump over to Excel and calculate one of these ourselves. So here in the Excel statistics workbook, I'm going to jump to the link on confidence intervals with the t-distribution. And we want to calculate the same question as before, but we're no longer assuming that we know the standard deviation of our population of employability scores after the program. So we're going to do everything just using our sample data. So let's calculate our sample statistics, the sample size, it's just the count of our values, the mean is the average, and the standard deviation is the standard deviation from the sample. Press enter, and now all we need to do is calculate the margin of error. We want a confidence level of 90%, which makes alpha 1 minus 90%, and alpha divided by 2, just alpha divided by 2. And for the critical value, we can use the t.m function, and we can either use alpha divided by 2, or I'm going to use, 1 minus alpha divided by 2. Let me specify my degrees of freedom, which is sample size minus 1. And we're going to get our positive critical value. Again, if I hadn't done this, I would have gotten the same number, just negative. Let me undo. And for the standard error, we have the standard deviation of the sample divided by the square root of the sample size. Press enter. And for the margin of error, we just multiply the critical value, which is number of standard deviations, times the standard deviation of our sample means. And we get a value of 15.94, which again, we could have actually just used the confidence.t function. We've got alpha, we've got our sample standard deviation, and we've got our sample size, and we get the same exact number. So for the confidence interval, we just grab our point estimate, subtract our margin of error, and then we grab the same point estimate and add the margin of error, and we get a confidence interval between 273 and 305. So that's where we can expect the true average of these employability scores to be with 90% confidence. And you'll notice that this is actually very similar to the confidence interval that we got when using the Z distribution. So instead of 274 to 304, we have 273 to 305. And the reason for that is that A, our sample standard deviation is actually very similar to the population standard deviation that we assumed. And B, our sample size is so large that the T distribution that we're using is almost identical to the Z distribution. Alright, I think you're ready for an assignment on confidence intervals with the T distribution. So Nick just got back to us and he wants to know if it's necessary to use the salary data from this study, because with the amount of graduates that have been placed already, he thinks that we can come up with an estimate ourselves just from the sample. So if you think you're up for it, here are the key objectives. Number 1, calculate the standard deviation from the sample of graduates. Number 2, set a confidence level. Number 3, calculate the margin of error. And number 4, set the limit for the confidence interval. So go ahead, give this a shot yourself, and then I'll see you in the solution video afterwards.